Today, we're going to pull back the curtain on a manufacturing process that is, well, it's pretty much all around us, but you almost never get to see it happen. We're going to explore how those beautiful, complex, and incredibly tough designs get fused directly onto the products we use every single day. So, let's dive in.
So, have you ever really looked at the intricate graphics on your car's dashboard, or maybe the seamless logo on a high-end appliance? You know it's not a sticker, and it's definitely not just painted on. So what is it? How do they get that perfect finish that, just doesn't peel, scratch, or fade away? Well, the answer is a really brilliant piece of engineering called in-mold finishing, or IMF for short. And honestly, the best way to think about it is like a recipe, a super precise, high-tech recipe for making a perfect product all in one go. So what is it exactly? At its heart, in-mold finishing combines making something and decorating it into one single elegant step. You take a decorative film, you place it inside a mold, and then you inject molten plastic right behind it. The heat and pressure from that injection permanently fuse the two together. You end up with one solid part, with the design literally built right into its surface. It's incredible.
Okay, so just like any great recipe, you've got to start with the right ingredients. For in-mold finishing, there are three main components that have to work together perfectly to get that flawless result.
First up, we have our substrate. That's the base plastic, the main body of the product. Then you've got the film. This is your decoration, your special coating. And finally, the tooling. You can think of this as the high-tech cookware, basically the mold where all the magic is going to happen. Now, the choice of that base plastic, the substrate, is absolutely crucial. For everyday stuff, like, say, a food container, you might use a common plastic like polypropylene. But for really high-performance parts, like something inside a computer chip factory, you need a way tougher plastic like PFA. The key here is that the base plastic is always chosen to match whatever job the final product has to do.
And this is where the product really gets its personality. The decorative film can be anything you can imagine. A solid color, a really complex pattern, something that looks exactly like wood grain or brushed metal. This layer gives the final part its look, its feel. But, and this is really cool, it can also be functional. Some of these films can actually conduct electricity, turning what looks like a simple plastic part into an electronic component. All right, so we've got our ingredients all lined up. Now let's walk through the actual cooking method. The entire IMF process happens inside the mold in this single, incredibly fast cycle.
Let's break it down. First, the decorative film is placed into the mold with robotic precision. Second, the mold snaps shut and preheats to get that film ready. Third, molten plastic is injected at super high speed. Fourth, intense heat and pressure fuse that film and plastic into one. And finally, fifth, the brand new part is cooled just right so it can be popped out. It's like this five-step dance of heat, pressure, and perfect timing. But here's the thing about that dance. Executing it perfectly is incredibly difficult. It is truly the difference between a masterpiece and, a total kitchen disaster. Getting a flawless product versus a piece of scrap plastic, it all comes down to controlling these tiny little variables at every single step.
This really gets to the heart of the challenge. Every single step has what are called critical control points. If just one of these is off, even by a little bit, it can mess up everything. How well the design sticks, how good it looks, and even the final shape and strength of the part.
Okay, let's start with just the placement. If that film is positioned perfectly, you get a beautiful, crisp graphic, just what you wanted. But what if it's off by, say, a fraction of a millimeter? The result is an obvious defect, an off-center logo, or maybe a part with uneven walls that could actually fail later under stress.
Then there's the temperature. This is such a delicate balance. You need enough heat to create a really strong permanent bond between the film and the plastic. But if you have too much heat, you can actually damage or overstretch that delicate decorative film, completely ruining the finish. It has to be just right.
Next up is the injection phase, and this is really the moment of truth. You've got three variables that have to be managed perfectly: the temperature of the molten plastic, the pressure it's injected with, and the speed at which it flows into the mold.
Because if any of those are wrong, you get two massive problems. First, you get a weak bond, which means that beautiful decorative layer could start to fail later on. And second, you trap a huge amount of stress inside the plastic, which can cause the part to warp or even crack over time.
And finally, you'd think once the part is formed, you're pretty much done, right? Not at all. The cooling phase is just as critical. If the part cools down uniformly, everything at the same rate, you get a stable, perfect product. But if one area cools down faster than another, that part is going to warp, and the film on the surface can get all distorted.
To stop this from happening, engineers use some seriously advanced strategies. I mean, they design molds with these cooling channels that snake all around the part, just to pull heat away evenly. They even integrate special cooling layers, or tiny gaps, to make sure there's total temperature control. This is precision engineering at its absolute finest.
So after all that, looking at the ingredients and all these super precise steps, let's just step back and ask the big question. Why go through all this trouble? Why does this whole recipe matter so much in the first place?
Well, when it comes down to it, in-mold finishing does three amazing things all at once. It creates products with these stunning, high-quality looks, it makes finishes that are incredibly durable because they're part of the product itself, and it does all of this in one hyper-efficient manufacturing cycle, which saves time, energy, and money, and that means we get more affordable and more intricately designed products.
And that leaves us with a pretty fascinating question for the future. We're already seeing this process used to integrate functional coatings, even simple electronics. So if we can build decoration, texture, and even function directly into the very structure of an object, just think, what are we going to make next?